Hi everyone, welcome to Modern Optimization Methods. Today we will introduce the third part of Chapter 8, the do problem. And recall that in this chapter, we are considering the abstract form of constraint optimization. That means we try to minimize fx, subject to that gx is in a cone k. Okay, here gx is a compact form of the constraint. Now, the do problem we defined as the following. So we first take the infimum of Lagrange function with respect to x, okay, in the whole space capital X. After that, then we try to take the supreme of Lagrange multiplier mu in the do cone K star, okay. So the do problem is actually we try to solve the supreme of theta mu with respect to mu in the do cone K star. Now, here we define theta mu to be the infimum of Lagrange function with respect to the primal variable x. And the Lagrange function is defined as the objective function minus the inner product of gx with mu, okay? So this is the definition for do problem. As you can see that for the do problem, the key point is how we can derive the infimum of Lagrange function. Another key point is that how we can get the do cone K star. Then normally this K star is easy to derive, okay? The key point is actually the infimum of Lagrange function for x. Now, let's take an example to show how we derive the do problem. Let's take the quadratic programming, for example. So in quadratic programming, we try to minimize the quadratic function x transpose qx plus c transpose x. We have some equality constraints ax equals b and have some inequality constraints here. Here we assume that q is positive definite, okay? And c, capital A, small b, capital B, and small d, they are all given matrix or vectors. Now, how we can derive the do problem? Let's use the abstract form. To use the abstract form, we still need to reformulate the constraints into gx in K. Okay, so gx actually include two blocks, the equality blocks here and also the inequality block bx minus d. The K, which is a cone, actually similar as in linear programming. It is a 0 point, and also then another block is the non-negative orthant. So we can easily derive that the do cone is the whole space of P and then multiplied by the non-negative orthant. So next, we can see that if we define the do parameter mu into two blocks, lambda and v, then lambda is in 4-dimensional space and v is in q-dimensional space. Then we have the following relationship for mu, which needs to lie in the do cone of K. There must be lambda free and also the v is non-negative. And for the feasibility condition, we require the equality and inequality holes, okay? So we write down the Lagrange function. The Lagrange function is actually takes the objective function, then minus the inner product of the two terms, gx and mu. Because g and mu, both of them, they have two blocks. So the two blocks here, they actually take inner product separately. So it can be equivalently written as inner product of ax minus b and lambda, as well as inner product of bx minus d and v. Okay? Then after that, we reformulate this function in terms of x, okay? Because we are trying to find the minimum of this function with respect to x. So we put x, the quadratic of x here, which is the quadratic term, and then the linear term of x here, okay? So notice that from this step to this step, we actually select the x item here, and then we do some transformations to move the coefficient to the next part, okay? Then this becomes the linear term about x here. The rest term are all constant with respect to x. After that, then we are ready to take infimum about x for this function. Notice that q here, we assume that it is positive definite, okay? So the Lagrange function with respect to x is actually a strict quadratic function. And the optimal value is achieved at the stationary point, which actually means the gradient of Lagrange function to be 0, okay? So if we take the gradient of Lagrange function to be 0, then we get the following conditions here, where we can see that qx is actually equals to a constant vector. So assume that q is positive definite, then we can get the solution for x star, which is the inverse multiplied by the right-hand side vector. Now we get the optimal solution for Lagrange function with respect to x, okay? Then we substitute this minimizer into the Lagrange function, then we get the optimal function value as L at x star with parameter mu. So we substitute x star into the formula, then after we reformulate and do some reformulation, then we can have the following result. So this is the dual objective function. And as you can see that in this dual objective function, x is cancelled out because we already substitute it by lambda and v. And there is only variable lambda and v. Both of them are Lagrange multipliers. Then the dual problem is actually that we try to take the supreme of the dual function theta, where the variable lambda and v should lie in the dual cone k star, okay? So we define the dual function as the form of this, right? This is what we have derived. We denote it as theta, then we can get the dual problem is this. So we maximize the theta function subject to some non-negative constraint about vector v. This is the dual problem, okay? Now, a question is here. When we derive the dual problem, we assumed that the matrix Q is positive definite. So if the Q matrix is only positive semi-definite, so how can we derive the dual problem? This is a very interesting question, and actually it was just recently answered by Professor Defeng Sun and his research group. So we can use, or we can define the restricted Wolf dual problem, and using the technique as well as the symmetric Gaussian-Seidel decomposition, then we can derive the dual problem in the case that Q is only positive semi-definite. So you can refer to the paper here to get more details about how we do the derivation for the do problem. Okay? Next, before we end this chapter, we introduce more tools for future use to derive the do problem. The one tool is called the indicator function for set C. The indicator function is defined as following. If a point x is an element in C, then the function value is defined to be 0. Otherwise, if x is not in C, then we define this function value to be positive infinity. Okay? So by this indicator function, actually for any constraint optimization problem, we can always transfer it into unconstrained problem by using the indicator function. For example, we have minimized function f, where this x is in a feasible set omega. Then by indicator function delta over the set omega, then we can get that this problem can be transferred into an unconstrained problem. Next, we will introduce the conjugate function of function f at a point x star. Okay? So the conjugate function at x star is defined as following. So the notation as f star at x star. The function value is actually a supreme of the following formula. So this supreme is to take the inner product of x and x star minus fx star. Okay? So for this formula or this function, we take the supreme over all x. Then the resulting function value will be the conjugate function value at x star. Okay? So for x star, it is actually lies in the do space of x. Okay? So this is the conjugate function about f at x star. Actually, this conjugate function is very important in deriving do problem. So when we have some very complicated case of constraint optimization problem, we need to use conjugate function and indicator function to derive the do problem and design more efficient algorithms. Now, let's make a brief summary about this part. In this part, we actually introduce the do problem from the abstract form of view, and we demonstrate by a quadratic example to show how we derive the do problem using the abstract form. Finally, we also introduce indicator function and conjugate function for future use to derive complicated optimization problems. Now, let's make a brief summary about this chapter. In order to deal with more complicated optimization problems, we discuss the abstract form of KKT conditions and do problems. Hopefully, these tools will help you to deal with more complicated problems. Okay, we stop here and see you next time.